Okay, so this question says let G be a graph with n vertices. G be a graph with the number of vertices is equals to n and number of edges is equals to m. What is the tightest upper bound on running time of DFS on G when G is represented as an adjacency matrix? So we know basically DFS takes big O of m plus n time when the graph is represented using adjacency list. We'll talk about adjacency list in a while. Big O of m plus n time using adjacency list. Okay, so adjacency list is nothing but a matrix representation. In adjacency matrix representation, graph is represented as n cross n matrix. To do DFS, every vertex we traverse the row corresponding to that vertex to find all adjacency vertices. So adjacency list works like a n cross n, whatever like number of n cross n adjacency matrices, right? To do DFS, every vertex we traverse the row corresponding to that vertex to find all adjacency vertices, right? So to do DFS, for DFS, for DFS, for every vertex we traverse the row. We traverse the row for every vertex. Let's say for this vertex, vertex B1, we traverse the row corresponding to that vertex to find all adjacency vertices. Like it's something like, let's say V1, V2, V3. For this we have 1, 2, 3, 4, 5, 6, 7, 8, 9. Like these are all the adjacency vertices for V1. So basically adjacency list and matrix, adjacency matrix, they're different. They're not equal. Okay, they're not equal. So to do DFS for every vertex, like we traverse for row corresponding to that vertex to find all adjacency vertices. Like in case of adjacency list, in adjacency list representation, we only traverse the adjacent vertices of the vertices. Therefore, time complexity is big O of n square. Because we are talking about the tightest upper bound. So we will take the time complexity for adjacency matrices, not for adjacency list. So C is the answer. So let me give you an example of adjacency matrix. So adjacency matrix will work like this. Let's say this node is A, this node is B, this node is C, this node is D, and another edge there is between B and D. So adjacency matrix will be something like A, B, C, D, A, B, C, D, AA 0, AB 1, AC 0, A and D 1. Why this is 0 and 0? Because from uh, A to C there is no edge. So A to C is 0 and from A to A there is no self loop. So this is also 0. B to A 1, B to C. Let me fill this up first. Okay, so this is the matrix after filling. This will become the adjacency matrix for this graph. Now let's see an example of adjacency list. Adjacency list. Okay, we'll take the similar graph for adjacency list also, and we'll show you how to create the adjacency list with from a graph. Okay, so for an undirected graph, adjacency list will be something like linked list. This is, let's say, A, this is B, this is C, this is D. And from A we have B, right? And from B from B we will only go to D. We can't go to B to C because A is not connected with C. Okay. Similarly, from B we can go to uh, C or D. But as we have went from A to B, so we'll go from B to A, and from A we can only go to D because B is also connected with D, A is also connected with D. From C we'll go to D, from C we will go to D, and from D we'll go to B, right? And from D we can go to all the edges. From D we can go to A, B, and C because D is connected with all the vertices, right? So this will be the adjacency list for an undirected graph. So we can easily see that this is something like linked list, and this can be done in big O of n plus n. But when we are creating matrix, this can be only done in big O of n squared. So as the upper bound is n squared, so C is the answer.